Golden Gate Assembly, the DNA hack you didn't know you needed. Welcome to Lab Survival Guide, helping you navigate the beautiful chaos of molecular biology. Disclaimer: no restriction sites were harmed in the making of this presentation. Yep, I lost it. This is not a substitute for official protocols or safety training. I am totally independent, no NEB, Thermo Fisher, or other company endorsements. My aim is making Golden Gate feel like building Lego. Buckle the F up. This is an advanced protocol, a real deep dive. By the end, you'll absolutely nail the assembly. Maybe not 52 fragments at once, but let's say a lot. Because why stop at sanity? It was invented in 2008 by Engler and her team. Golden Gate Assembly, it's a one-pot reaction that lets you assemble DNA fragments in a defined order, leaving no scars. It uses two enzymes at once, type 2S restriction enzyme and ligase. Let's look at type 2S restriction enzymes. They recognize an isometric DNA sequences but cut outside their recognition site at a defined distance. Since this distance differs for each enzyme, spacing is a key factor in DNA assembly design. The enzyme binds to the DNA and cuts it. Both the recognition sequence and the cut site stay behind in the discarded fragment, while your piece is left with the perfect overhangs, ready for assembly. Type 2S enzymes create 1 to 5 bases overhangs, enabling precise assembly of multiple DNA fragments. 4 base overhangs can produce up to 256 unique combinations, demonstrating how careful design simplifies complex assembly. And now let's talk of the ligase, which is used to join the fragments. The T4 DNA ligase joins the cohesive ends of 2 compatible overhangs and repairs the nicks, resulting in a continuous and stable molecule. How do we create the assembly fragments? It's like Tetris. You have to think about the enzyme's orientation or the pieces won't fit. Get this wrong, and your assembly won't stand a chance to work. The 3' end of one fragment becomes the 5' end of the next. The enzyme at the 5' end is in the sense orientation. The one at the 3' end is in reverse complementary orientation. Both enzyme sites are placed outside your assembly fragment. Simple and efficient, just how we like it. First, identify 5 and 3' ends. These are a backbone and an insert for your assembly. The fragments you want to assemble are highlighted in blue. The red arrows mark the start of each fragment, and the green mark the end. So the forward primer is designed on the 5' strand, at the start of the molecule, while the reverse is designed on the 3' complementary strand at the end of the molecule. Now imagine you need to design primers for this fragment. Only the 5 and 3' ends are shown. For the forward primer, for example, the overhang you want at the 5' end is CCAT. Well, guess what? This is the cut site. Place the type 2S recognition site before this overhang. Ensure the recognition site is positioned at the correct distance from the cut site. The forward primer will span from the recognition site to the target sequence. Now, for the reverse primer. This time the overhang you want is GGTA. Place the type 2S recognition site, this time after this overhang, in reverse complement orientation. Remember to include the spacer. Even this primer will span from the recognition site to the target sequence, but in reverse complement orientation. Remember to add at least 6 bases before the binding site. The cut site itself is removed with a recognition sequence, leaving behind the desired overhangs for assembly. And now few rules. When assembling more than 2 fragments, don't use the same overhang twice. Avoid palindromes. Do not use 3 identical bases on the same overhang. No more than 2 identical bases in the same position. Mind the GC%. Overhangs differing by only 1 base will ligate. Remove internal type 2S sites. Create the molecule in silico before starting the cloning. Assign unique overhangs to each fragment. When possible, use the most efficient overhang sequences. And now the protocol. Aside from DNA parts and the enzyme, you'll also need reaction buffer and ligase, or you can use a commercial pre-made mix for simplicity. You will also need PCR tubes and a thermocycler. When it comes to vector insert and enzyme concentrations, the conditions vary. However, as general guidance, vector 50 to 100 nanograms, insert molar ratio from 1 to 1 to 1 to 10, enzyme between 10 and 30 units. Who needs specifics when you have vague advice? This general reaction protocol is based on a commercial pre-made mix. Always refer to the supplier's instructions. If you are not using a pre-made mix, you must add the volumes of buffer and ligase. Prepare the reaction on ice in PCR tubes. Include an empty vector control assembly and begin the assembly protocol. The assembly conditions depend on the enzyme used and the number of fragments involved. The table lists the most commonly used enzymes. When using BSMB1 and BSPQ1, set the temperature to 42 degrees Celsius. Keep in mind that at this temperature, both the enzyme and T4 ligase have reduced activity, so the protocol is longer for effective assembly. Always check the enzyme's optimal temperature for the best results. Let me know if you'd like more tips. To increase efficiency, you must inactivate the enzymes at the end of the cycling. Heat the sample to 60 degrees for 5 minutes. This step is required before every transformation, even for samples stored at -20 degrees. Now is the perfect moment to sit down and enjoy that well-deserved break. Now, my tricks. These are based on my own experience. They work for me, so take them as tips, not official recommendations. Always check the manufacturer's instructions first. Imagine this mess. Tons of vectors and inserts all over the place, and they are all different sizes. Do you really want to calculate all the molar ratios? Dilute each vector and inserts to a concentration of 60 nanograms per microliter. Use 0.5 microliters in your reaction to provide 30 nanograms of each fragment. This has consistently worked well for me regardless of the number or size of fragments. Additionally, this approach keeps the reaction volume low, making it especially useful when assembling more than 6 fragments. I choose 60 nanograms per microliter since 0.5 microliter is a comfortable volume to pipette. Of course, you can choose whichever initial concentration is convenient for you. Do you have crappy fragments? Your fragments are bad, really bad, but you're stuck with them. Even imperfect fragments are included, no pun intended. You can use 10 to 15 nanograms per fragment. Or you can run 60 cycles, each assembly temperature lasting 5 minutes. Or even, why not do both? Tools like NEB, Snapgene, and Genius are great. Just tell them where to join your fragments. Last advice. You might think that following the protocol to the letter is the key to success. Well, not all the times. Every company says it. You have to optimize the protocol. There's no such thing as a perfect procedure. You make it perfect for you. Don't be afraid to explore. You've made it to the end. Didn't I warn you this would take forever? Thanks for watching. Lab Survival Guide. Keeping your DNA in line and your sanity intact. DNA runs on caffeine. I run on hope. And my cat runs away unless you subscribe.